Hello everybody. This session is on Google Compute Engine and MongoDB by Mark Helmstetter. Mark is a senior solutions architect for MongoDB. Before joining MongoDB, Mark was a senior principal consultant at Mark Logic, where he supported large-scale deployment, providing sales support, training, design, development, performance tuning, and operation support for federal customers. Mark spent most of his career designing and developing database-driven applications in both public and private sectors. Please welcome Mark.
Thanks, guys. So it looks like I am standing between you and lunch, but there is cold beer outside. It looks like a lot of people have already indulged. It's Friday, so good day for that. So yeah, thanks for the introduction. Today I'm going to talk about Google Compute Engine and MongoDB. Quick show of hands, how many people here today are users of MongoDB and are familiar with it? Oh, pretty good. Anyone who's brand new or never used MongoDB? Cool. All right. Looks like we're about 50-50 or 60-40, something like that. So quick agenda overview. So I'm going to start with a quick overview of MongoDB for those of you who are not familiar with what MongoDB is. Then I'm going to give an overview of the Google Compute Engine, or GCE. And then we'll talk about the marriage of GCE and MongoDB, running MongoDB on top of the Google Compute Engine platform. So MongoDB is an open source, non-relational, so-called NoSQL database. It's a document-based database. When we talk about documents, we're talking about JSON documents. We're not talking about Word documents or PDF documents. All of your data in MongoDB is represented as JSON documents. JSON is JavaScript object notation. Actually, under the covers, internally, we're storing your data as what we call BSON. You can go to bsonspec.org to get all the details, but basically, BSON extends JSON, adding additional data type capabilities. So we add a datetime data type, we add a binary data type, all the numeric data types that you would expect, in addition to, of course, strings, integers, things like that. So that's how everything in MongoDB is stored as JSON. So MongoDB has been, as an open source database in the NoSQL world, has been hugely successful. We've had more than 8 million downloads of the product by judge of the room. A lot of people are already using it. And I think the #1 reason by that is developers love MongoDB because it's easy to use. So Mongo provides greater agility, faster development cycles by just not getting in your way. And one of the ways that we facilitate that is through what I like to call dynamic schema. So when you store these JSON documents in MongoDB, we don't force you to define the schema of what you're storing. You take those documents and you store them in a bucket called a collection, which is roughly analogous to a table, and you can store whatever you want. So every document in the collection could be different. Now in practice, most of the documents are going to be similar. That gives you a lot of agility so that as you evolve your application, if you're loading legacy data, you can have a combination of legacy data and new data. Some documents may have certain fields that other documents may not have. The other 3 reasons why MongoDB has been so popular is basically performance, high availability, and scalability. So we can scale to millions of operations per second. We offer high availability through replication, so you can have 24/7, 365 operations. You can do things like rolling upgrades to your application without downtime by having multiple copies of your data via replication. And when we talk about scale, we're talking about petabytes of data. So we have customers who are running very large clusters of MongoDB, storing petabytes of data in production. So the other thing that makes MongoDB so easy to use and so quick to get started is that regardless of what programming language you're using, so whether you're using Java or Ruby or Python or .NET, we provide a native driver that has an API that is very sort of natural to that language. So if you're working in Python, you're probably just taking a dictionary, a Python dictionary, and storing that into MongoDB via the Python driver. So bottom line is, no matter what programming language you're using, there's probably a driver available. I've separated this slide so the top section of drivers are drivers that MongoDB develops and are the officially supported drivers. There are, because we're open source and the specification is public, there are other open source implementations for some legacy languages like, I don't know, Delphi, and other drivers for newer upcoming languages as well. So in addition to the drivers, there's a very large ecosystem sort of built on top of MongoDB. So the drivers kind of provide sort of a lower level API in terms of how you interact with MongoDB. There are a lot of other tools and frameworks that provide higher levels of abstraction in terms of how you interact with the database. A good example for this is what we usually call an ODM, or an object document mapper, which is somewhat analogous to an ORM framework like a Hibernate, which basically allows you to take an object in an object-oriented language, sprinkle a few annotations on it, and just take that object and store it directly into MongoDB. Other frameworks out there, like your basic MVC type frameworks that have integration with MongoDB, other persistence APIs that provide an implementation where you can plug MongoDB in as a backend. So here's at the top here's a basic schema entity relationship diagram. Let's say we were implementing a very simple online ordering system. We might have 4 tables in our relational database. So we might have an order table, which has an order ID, customer ID, a date. And for that order, in order to store the line item for each individual order, we have to have a separate table, where we might have a compound primary key consisting of the order ID and the order item ID, and then the product associated with that and the quantity of the product. When you model data in a document-oriented database like MongoDB, your data modeling or schema design is going to follow a very different pattern than what you might be used to in the relational world. So here, we're going to take a much more, I like to think it's a much more intuitive view of the document. So we have a very rich JSON document. So we have an underscore ID, which is our primary key. By default, MongoDB will provide an index for that. And then we have all of our additional fields. We have our customer ID, our date, and for our order items, we can actually store an array. And that array of ordered items is an array of objects or an array of JSON subdocuments. So if you imagine that you were building this online application, and let's say we were building the order summary screen, everything that I would need to display that order summary screen can be accomplished by one query. So everything that I need for that particular application view is all within this JSON document. So for developers, it's much easier to develop. From a performance perspective, having all that data in one place on disk without the need of expensive joins makes it very efficient. And if you've ever walked into a DBA's cube and seen something like this, understanding your data model is much, much easier. I mean, this is a real, I think this is actually Magento CMS is where this schema came from. So this is actually very near and dear to me. I started my career working with relational databases. I was a DBA. I worked in Irwin designing relational databases for an online advertising system and also for a point of sales company. And I lived building these things. But developers hated me, whenever they came to me with a concept and I came back with a design and they were like, what is this? I can't make sense of this. Just to find the data, you have to query across all these tables. And there's just a lot of complexity associated with that. So querying in MongoDB, so because we're a NoSQL database, we don't provide a SQL interface to the database. But what we do provide is a very simple query API. So what I'm showing here is the Mongo shell. And the way you query in MongoDB is essentially query by example. So you provide an exemplar JSON document that defines all of the specific criteria for your query, pass that to find. What you'll get back from that is a cursor, just like you're used to in other database type APIs. In this case, the Mongo shell will actually automatically iterate the first 10 results for you, and this is actually the pretty printed result of querying. So I'm querying on customer ID 456, and this is what I would get back in the Mongo shell. The API for whichever language driver that you're using would be very similar. So you would maybe construct an object, pass it to that has the criteria that you need, pass that to find, and you would get back an object representing the orders. Indexing in MongoDB, I like to say indexing works very similarly in many ways to how indexing works in a relational database. So unlike some other NoSQL databases, key value stores, things like that, we offer a rich indexing capability. So you're not just retrieving a document by its primary key, its underscore ID. You can create any number of secondary indexes, so you can support multiple use cases or multiple ways of retrieving your data. So I might create a compound index on customer ID and date to retrieve the most recent 10 orders for this particular customer, so I can efficiently get back that result set sorted descending by date. You can index embedded documents, so you have these deeply nested JSON documents. You can index fields within those nested objects. You can also create multi-key indexes, so if you have an array of entries, you can index the items within that array and query based on that field. We also provide geospatial indexes, so if you're building some kind of location-based application or service, you can take advantage of that. And we also offer full-text indexes, so you can do text queries. So you can create the full-text index on specific fields within the JSON document, or use a wildcard and create a full-text index on all of the fields in the document. Okay, so scalability. So we accomplish horizontal scalability by partitioning your data set into individual shards. So each shard itself is a commodity server that has some subset of the data. So from an administrative perspective, you define something called the shard key, which is how MongoDB decides how to distribute that data horizontally across those shards. So sharding is not a new concept. It's been around for quite a while. You can build application level sharding, but in MongoDB, we sort of take care of all of the mechanics for that for you. So from your application perspective, whether you're talking to a single instance of MongoDB or 1,000 instances of MongoDB, the way you interact with that is very much the same. This allows you to increase or decrease capacity as you go. So if you provision too much capacity, you can take shards away. And as you grow, you can add shards. And MongoDB will take care of balancing that data across those shards as you add additional capacity. So you can scale up or scale down. You can do this on bare metal. You can do this on any of the cloud infrastructures. And of course, I'm going to talk about Google Compute Engine in that context here in a moment. From a high availability perspective, we provide replication through what we call replica sets. So a replica set is a pretty basic concept where you're going to have 2 or more copies of your data. For the most part, we typically recommend that you have at least 3 members, at least 3 copies of your data for replication. What I'm going to show a little bit later is sort of the minimal configuration, where you can actually just have 2 copies of the data and a third node called an arbiter. And the arbiter is just a lightweight process that participates in the elections. So basically what's happening here is the nodes are exchanging a heartbeat among each other. So they're going to automatically detect failure. If a node fails and that node is the primary, then a new primary will get elected. So the reason why we have 3 nodes is if we only had 2, then you sort of could end up with a sort of a split brain situation where you can't hold an election to get a majority. This works, again, very well for high availability, disaster recovery. It also, from a maintenance perspective, you can do rolling upgrades. So if you need to do OS patches, hardware upgrades, whatnot, you can actually, in a rolling fashion, go through, take a node out, do your maintenance, and then bring it back in. When we're talking about high availability and cloud infrastructure, you can take advantage of the fact that providers like Google Compute Engine have multiple data centers and multiple geographic zones. So we can place a MongoDB node in different data centers and in different geographic regions, and we can construct a replica set to basically connect to that. And this is potentially one architecture that you might use. So you could have an application server in each individual data center, and you could use, Google Compute Engine provides load balancing capabilities, so you could let them provide the load balancing. Inside of the MongoDB driver, you can specify something called a read preference. So you can say, I want to connect to the MongoDB instance that has the lowest ping time. Or you can just have it have a specific MongoDB instance that you want it to connect to. This is just one sample deployment on how you might use MongoDB in a multi-zone, multi-data center deployment. Right, so things get more interesting when you start to combine replication and sharding. Well, actually, if you are sharding your data, you have your data spread across multiple machines, and you were to suffer a machine failure, well, part of your data just went offline or just disappeared, right? So in practice, for a production deployment, each shard should itself be a replica set so that you can suffer a failure of a member from that particular shard and still have your data be available and online. This is done, basically there's a router process called MongoS. MongoS knows the distribution of data across the shards. And when you issue a query through the driver to MongoDB, the router knows if the query contains the shard key, the router knows how to route that to the node or nodes that contains the data that you've asked for. If your query does not contain the shard key, the router does what we call a scatter-gather query, where it essentially broadcasts the query to all of the nodes in the cluster, takes all the data back, and essentially does a distributed merge sort of the result set. All right, so let's move on and talk about Google Compute Engine. So you may have already heard of a few presentations or mentions of Google Compute Engine today. In a nutshell, it is infrastructure as a service. It's very similar. I don't know if there's any Googlers in the room here, but it's very similar to offerings from Amazon, Microsoft, Rackspace, other cloud hosting providers. And basically, Google Compute Engine gives you virtual machines. It gives you persistent storage or disks. It gives you networking and firewall capabilities, and also load balancing capabilities. So why Google Compute Engine? Well, basically, this is what one of the Google data centers looks like. You want to leverage the infrastructure that Google has invested in, right? So Google owns pretty much the entire infrastructure. And you want to leverage that scale and performance that Google has. You want to be able to quickly spin up VMs and spin them down. So maybe you just have a short test that you need to run. You can spin up 5 or 10 or 100 VMs, run your test, spin them down, and hopefully it didn't cost you a fortune doing that. Again, you can also take advantage of the fact that Google has data centers around the world, and have your application be geographically available with minimal latency. So Google Compute Engine, this is very useful for pretty much any type of environment that you might want to stand up. Maybe you're going to use this for your production, Maybe you're going to use something else for production and use Google Compute for your development and test instances. It's a very good environment if you want to do a quick load test, right? Spin up a couple hundred instances and run your load test and find out where the bottlenecks are. It's great for demos. Maybe you have a customer demo. You can spin up a couple VMs, have a separated instance just for each customer demo. It's great for prototyping. It's also great for troubleshooting, right? So a customer calls you up and says, hey, I'm running CentOS 6.5 and running your software, and I have this problem. In a couple minutes, you can spin up a CentOS 6.5 instance and start to reproduce that particular problem. So you have a lot of choices in terms of instance types. There's really 4 major categories. You have a small micro instance, which only has 1 vCPU, and you have your standard high memory and high CPU instances. As far as MongoDB goes, typically we recommend using standard or high memory instances. You have a choice between generally between 2 and 16 virtual CPUs, and RAM as high as 104 gigabytes per instance. We generally don't recommend a high CPU instance. Those are pretty much the same as high memory, except they're very anemic on the memory side, maximum of 14.4 gigabytes of RAM, which is not ideal for running a large database. Generally, MongoDB is not going to be CPU bound anyway, so it doesn't really make sense to bulk up on CPU. You'd be better off spending your money on memory and disk. So persistent disk. Persistent disk is really kind of like just a logical disk drive that's spread across lots of physical drives within Google's infrastructure. Google has already taken care of the striping across many different physical drives, and they've already taken care of the redundancy for you. So you don't really need to put RAID on top of this because they've already taken care of that under the covers. And basically, your IOPS, the number of I/O operations per second, are going to be throttled, and your throughput is going to be limited based on the size of your virtual machine. So you have a choice between standard spinning disk or SSD, and you can go as high as 15,000 write IOPS or 10,000 read IOPS for an SSD. And basically the throughput scales as the size of the volume scales. So in order to get the maximum number of IOPS, you have to have a very large drive, basically. Google also caps the network egress on your virtual machines. So basically 2 gigabits per second per core. So the number of cores is going to cap that. And so your write operations to persistent disk are going to be combined with your network I/O and contribute towards that cap. When you do these calculations, because of the redundancy, you have to take each write operation is 3.3 network I/Os. So long story short, in order to get to the full capacity, say with SSD, you need to have at least 500. I'm sorry, at least 4 cores and generally a 500 gigabyte volume in order to get the maximum amount of throughput that device can achieve. So when you deploy in Google Compute Engine, you have a couple of different options. They have a click to deploy, so you can go to the console, you can click a button, and it'll deploy a VM instance for you. They also have the capability to click a button and deploy a MongoDB cluster, which I'm going to show you in just a minute. They also provide a cloud SDK, which is very easy to download and set up. That includes a command line tool and also REST API and client libraries. So you can build a sort of deployment tool, if you like, or script it using your favorite language to script your particular deployment. You can also use Chef to orchestrate the deployment of your infrastructure. So click to deploy MongoDB. I'm going to show that in just a moment. This allows you to quickly stand up a single replica set on top of Google Compute Engine. By default, it's going to spin up 2 4-core data-bearing nodes with 26 gigs of RAM and 1,000 gigabytes of disk. And it'll spin up a single, an Arbiter instance that's just a very small micro instance, I believe, for the Arbiter. So let's see if I can show a quick live demo of this. Right, so this is what the Google Developers Console looks like. You can basically sign up. I think they'll give you $300 of free credit if you sign up. I'm using someone else's expense account in my case. Everything in the Cloud Console is associated with a project. So you manage all of your users and all your resources. The project is sort of the top level container for your particular resources. So I have one project called Petamongo. I can click on that project and see what my usage is. And down in the left menu, you can see here where I can go to VM instances. So I can click to deploy a specific VM instance. Or if you go to the click deploy down there at the very bottom, there are a number of popular software packages out there, and MongoDB is one of them. So I can go to the MongoDB page. It tells you a little bit about what this is going to configure, which is basically what I told you: a primary, a secondary, and an arbiter. You have a basic configuration. You can just accept this basic configuration and click it to deploy. There are some advanced options that they provide, so you can change the node count. So maybe I want 5-factor replication. I can increase my number of nodes to 5 and have 5 data-bearing nodes. I can change my disk type to between standard and SSD. I can increase or decrease the size of my data volume. I can specify what version of MongoDB I would like to deploy, what instance type I would like to use, et cetera, et cetera. When you're all done, just click Deploy Cluster. And it's probably kind of small, but basically it says deployment may take 3 to 10 minutes. So let's just wait 3 to 10 minutes. There's no hurry, right?
So do you know the cost of this, what you have just done?
It's cheap. It's dirt cheap. I think you saw on the previous page I racked up like $20 worth of stuff over a couple of days with light usage.
No traffic or with traffic?
So they don't like, you don't necessarily pay by the drink. So you pay for how big your virtual machine is, and you pay for how much disk space you have. But you're not paying for like CPU cycles or bandwidth or anything like that. I mean, it's capped, but you're not paying for that. You're paying a fixed price, right? So the calculator, you can use the online calculator to calculate it. We actually internally we have a project called Petamongo, which this is part of, and someone at MongoDB wrote this tool to stand up basically a petabyte scale MongoDB instance. And we did this on Google Compute Engine, and we did overrun our budget a little bit. I won't give any specific numbers, but someone didn't calculate out how much it was going to cost. So definitely use the calculators to figure out how much it's going to cost. But for just a small VM instance, it's pretty cheap and it's easy. But I like to use it really just for quick tests. So I like to spin up a 5-10 node cluster. Run it for a day or a week, and then shut it down.
Yeah, are the instances of MongoDB that's stood up on this, are they several revs back, or can you get the latest rev of MongoDB?
Right. So the question is, what version of MongoDB are these instances? And so this click to deploy thing that I'm using here only gave me 2 choices, which was 2.4.9. And 2.6.3. So those are not the latest and greatest. Particularly the 2.6 version is a couple revs behind. So probably need to talk to Google about that and see what their plan is to keep those revisions up to date. The other option that you have is to just spin up the VM on your own, and you have so attach the disks, spin up the VM, install whatever you want. So install MongoDB Enterprise version 2.8 if you want to be crazy. 2.8 RC0 just came out about a week ago. So that gives you full control.
Do we have any support cost for the MongoDB which runs on the instance, or it is just the compute cycle for the Google instance?
So you're asking if you can get MongoDB support?
Do we have a support, and is there an associated cost involved? Or
Oh,
if
yeah.
I just deploy whatever you showed on a Google instance, is it what just I pay to the Google, or
Yeah.
is there an
Yeah, you're not paying. You're not in this case. You're not paying anything to MongoDB. So
it's all associated cost?
yeah, it's all with Google. So your support would go through Google. They're actually running. So there are actually two versions of MongoDB. There's the community version of MongoDB, which is basically the open source version. There is an enterprise version of MongoDB, which is what pays my salary. And that's where you get support from MongoDB. So if you had a support contract with MongoDB, you could get support through MongoDB on Google Compute Platform.
Version which is available here are both the versions, or just
The version that they're using here is the community edition. If you want to install MongoDB Enterprise, then spin up your own instances on Google Compute and install MongoDB Enterprise, which is what I do.
So I've used MongoDB, for several projects. However, I've also used Postgres a lot. So Postgres now is about to start. I think their last version came out with GCE. And so, how does the MongoDB team feel about that? Because I keep on hearing that's a game changer.
So the question is MongoDB versus Postgres' new support for JSON. I have to be honest, I have not. MongoDB does write my paychecks. I haven't spent a lot of time messing. I mean, I've used Postgres in the past, and I don't run into it a lot. My customers aren't asking about it a whole lot. It is pretty new. I think the capability is fairly immature, but I don't know a whole lot more than that. The database space. I mean, databases. The database space is pretty hot right now, right? So there are a lot of databases out there, and I think the good thing about MongoDB is that from a NoSQL perspective, I mean, we have the most critical mass, right? So if you take all the other NoSQL databases and combine them together, they're about the size of what MongoDB is. So lots of developers out there know MongoDB. That's an advantage for you. Lots of people are using MongoDB, shaking out the bugs. That's an advantage for you. Lots of big ecosystem built around MongoDB. That's an advantage for you as well.
So one thing is about the linking between the documents, right? So MongoDB, how do you feel about the linking of different types of data? What kind of support?
Right. So the question is about the linking of documents. So when you schema design in the NoSQL, so I've been working with NoSQL databases for about the last 8 years, and doing document-based schema design is very different from how you do it in the relational world, right? In the relational world, there's a pretty clear pattern in terms of how you normalize your data and how you come up with a schema. When you do it with a document-based database, you really have to start by looking at your use cases and looking at your access patterns and come up with a schema design that sort of meets your access patterns. So in some cases, that might be a combination of embedding linked data directly in the document, as well as storing it in a separate document. So I like to, a lot of times, again, back to the order summary page, I like to think about, okay, what information do I need to display this page, and think about how I'm going to structure it accordingly. Another good example of this is, let's say you're building a blogging system, right? So a blog, you have a simple blog post. It's just a clob of text, and then you have the comments on your blog post, right? So a very simple schema design would be to just embed those comments within the blog post document, right? So you can just do one query to render that page. Well, what happens if your blog post goes viral and 10 million people comment on your blog post, right? So now you've got this massive, massive JSON document that keeps growing and growing and growing and growing, and that's not good, right? Because that's going to be one big I/O when you go there. Nobody, when they go to your blog post, is going to read all 10 million comments, right? So a common approach is to basically bucket the data. So what are you going to display? You're probably going to display the 10 most recent comments, or maybe you're going to display the 10 most popular comments. So you could take those and store those directly in your blog post document, but then additional posts outside of that you may store in a separate comments collection and retrieve those that way. So sometimes a hybrid approach works very well.
So then, actually, to build on that, so I know there's a 16 megabyte limit for documents. Is that ever going to change? And on top of that, I forgot that. But yeah, 16 megabyte limit for a document.
So 16 megabyte, yes, there is a 16 megabyte limit for a document. It's there for a reason. You could change it. You could compile your own version of MongoDB and change it. I'm pretty sure you can do that. But I wouldn't do that, right? So if you get up to 16 megabytes, again, you know what? So what is your use case, right? If you're building a web application, if a user is accessing 16 megabytes of data in one chunk, that's kind of I would start to question that. So so you need to be aware of that, and from a performance perspective, you need to totally lost my train of thought.
Oh, that's the other thing. So querying subsets of data. So I want to store all this in a document because I want to keep everything together, and then actually querying subsets of that document. Is that supported, or?
So you can, so querying subsets of a document, so you can query based on any field, no matter how deeply it's nested, but you can provide a projection of the data that you want back, so you can restrict what actually gets returned by your query. So instead of select star from orders, you can say select order ID date from orders. So you can project what you want to get back. I think that's what you mean.
Yeah.
Sorry, there's a question?
How do you get, like, how you dump the data into MongoDB?
How do you dump data into MongoDB? So there are a number of tools. There's a tool called Mongo Import that can take JSON data or CSV data.
Kind of flat by defining the metadata on MongoDB, and it automatically reads the primary keys and creates the JSON.
Yeah, I mean, if you want to get more advanced than that, then probably you're going to write a simple ETL tool, or use a tool like Pentaho or something like that, an ETL tool that integrates with MongoDB. But if you can get it in CSV format, you can load it into MongoDB. The thing that I would caution you of is if you're taking a dump from a relational database and loading it as is into MongoDB, that's going to work okay for very simple uses, but you know your data is, you've got a relational schema in MongoDB, so now you're going to have to do joins. So you need to kind of make sense of the data first, but before you actually load it in.
Do you have any recommendation for data visualization using MongoDB?
Data visualization using MongoDB. I mean, you know, JavaScript libraries. You know, you can use any number of JavaScript libraries. As far as commercial products, you know, click.
But then you have to have the aggregate numbers. How do you have aggregate numbers?
Oh, so the aggregation. So MongoDB has something called the aggregation framework. You can run directly against your data inside of MongoDB. Lets you do the sort of typical aggregation type queries. So, you know, sum, count, min, max, average, group by, all that kind of stuff you can express using a simple declarative construct for aggregating your data.
So if you were importing a large relational data set into MongoDB, would you just flatten it out and then suck it into MongoDB? How do you do it?
Okay. So question is importing a large relational database into MongoDB, and would you just flatten it out and suck it into MongoDB? Yeah, that's much better than what I said previously, right? So you definitely not a good idea to take every individual table and load that into MongoDB as is. But you can, if you could take a dump from a view that already has what you call the flattened out view or the denormalized view, then that would be a much better starting point. But it's also, you may have hierarchical data that you want to represent, you have arrays, and so you need some way of, so how do you represent that join if you have, an array of order items? How do you export that to CSV? That's kind of hard. I mean, maybe, so again, it kind of goes back to building some sort of ETL process that knows how to build a JSON document that makes sense, that has an order with all the order items embedded in it, and suck that into MongoDB.
So if I had data in a structured data set, let's say a bunch of PDF documents, and I have no idea what the PDF documents contain, how do you write a query where you can mine both the structured information and the PDF information? Like, let's say I'm searching for customer name or a product name.
So I think you're talking about mining unstructured data. So you're talking about PDF documents, and you want to structured and unstructured, right? So I mean, there you're really talking more about sort of a full text search type scenario. So you could use the full text indexes. So you could extract, do text extraction from the PDF document and summarize and index that using the full text index. And you could do a combination of the metadata on the document and the full text on the document. Does GCE have Hadoop? GCE, so on the click to deploy page, back to, well, I don't want to go past this page, but yes, Hadoop is one of the click to deploy products that they offer, and you can do that. You can also integrate Hadoop with MongoDB, but yeah, that is an offering. So let me, we're getting a little tight on time. Let me just kind of wrap up this quick little demo here. So I clicked, and basically my instance is deployed. And now, in order to connect to this, I can SSH. There's a Google command to SSH to it, and that's how I would connect. We should be able to see the VM instances here in the page. So you can see there are 3 VMs that were deployed. There's the arbiter and the 2 data nodes. You can actually SSH directly here from the console via the browser, which is pretty cool. So just click.
How do you know the rows of the nodes? Looking at this.
Well, there are only 2 data nodes, so I have a 50-50 chance that I got the right one. Yeah, so when you're talking to a replica set, you can connect to the primary or the secondary, but you have to actually enable secondary reads in order to be able. So I just logged in through SSH via my browser. I typed Mongo. I'm in the Mongo shell. I can run a rs.status, and I can see that I have a primary, a secondary, and an arbiter. All of them look healthy, and I'm basically off and running here. Right. Okay, so let me just zip through this real quick. Okay, so the GCloud CLI, really simple to install. Just run the curl command, pipe that to bash. It'll run through a really simple installer. It'll set up your path for you, so you need to either open a new shell or source your bash profile. Then just a couple of simple commands, gcloud auth login to provide your authentication credentials, your Google authentication credentials. If you're doing this in a headless environment, add -- no auth browser that'll allow you to open the URL elsewhere and get back a token. Then I usually set these 2 parameters, so everything you're doing is in the context of a project. So instead of passing these parameters to all subsequent commands, just run gcloud config, set project to your current project. And then I like to set a zone because most of the commands require a zone. So gcloud config, set the zone. With that set up, now it's only one command to launch a virtual machine. Gcloud compute instances create, give it an instance name, provide any number of parameters, generally just machine type, tell it what OS you want. In this case, I'm asking for CentOS 6. And then just run GCloud compute SSH to connect to that instance via SSH. Here's a couple of resources. You can Google this if you don't want to write down these URLs that provide a tutorial on doing this step by step. If you want to learn more about MongoDB, university.mongodb.com/courses. We offer free online training. These courses are pretty awesome. We offer them in Python, Java, Node.js. I think those are the 3 primary languages. There's a developer's course and a DBA course. So check it out. There are a lot of books out there on MongoDB, some good O'Reilly books. MongoDB Definitive Guide is a good book to get started. The Manning book, MongoDB in Action, is good. I also like MongoDB Applied Design Patterns is a really good book if you want to learn more about schema design. So a lot of the questions that you guys are asking about different schemas, embedding versus linking, that's a great book that gives a lot of common examples like e-commerce applications, blogging applications, things like that. All right, so I'll take a few more questions.
I got one. This is regarding the 16 megabyte limit on the file size. Like when a file just keeps growing, is there something in MongoDB that tells you that it's about to reach the limit, or is that something I have to manage in my application?
Right, so the question is regarding the 16 megabyte limit. If the document keeps growing, is there something in MongoDB to warn you about that? Short answer is no. It's one of the considerations that you should make when you design a schema, because unbounded growth is not always a good thing, right? So MongoDB has a number of strategies for padding the allocation in memory and on disk, so that when you update that document, so we do updates in place. It's not like some other data stores that are pen only. The updates are actually in place. So if you update the document and you grow it, and you grow it, and you grow it, eventually you're going to outgrow that space on disk and that space in memory, and MongoDB has to move that to another location on disk, which is an expensive operation. So that's why, from a performance perspective, we try as much as possible to avoid unbounded growth. It's also a good idea to, if possible, to pre-allocate your document. So if you know that you're, say, recording time series data and you know how many hours and minutes there are in a day, and you're, say, collecting machine statistics, you can actually pre-allocate that whole data structure in MongoDB, and updates, because they're in place, are very fast and efficient. So 16 megabyte limit, you should design your application so that that isn't a problem. You should really take that into consideration. A lot of people, when they're new to MongoDB, really get hung up on that. And I think once you sort of learn a little bit more about schema design and learn how to structure things, you'll find that rarely does that 16 megabyte limit really come into play as something that's hard to deal with.
So I'm kind of new to Mongo, and I've only done simple kind of play or toy examples. If you are going to do time series data or something like that, what is the schema design strategy to mitigate that? You know, if you know you're going to be over 16 megabytes eventually, do you start paging that, or do you?
Yeah. So the question is about time series data in MongoDB. I actually.
Block comments or anything that you could grow.
Oh. So how do you deal with that? Or
Yeah. What's the schema design strategy to that?
I could talk for about 5 days on that topic. I mean, not to make it sound harder than what it is, but yeah, I mean, the strategy, I mean, you really have to carefully look at what your use case is, what your access patterns are, and kind of design based on that, right? So, you know, with time series data, you know, how are you retrieving the data? What is the granularity? Or do you need hour level granularity? Do you need minute level granularity? And there are different strategies for doing that. Maybe you need both, right? So maybe you store multiple copies of the data, but definitely, you know, the pre-allocation of data with time series data. If you know, you can basically pre-allocate a big structure in MongoDB with time series data, and deal with it that way. There are a lot of strategies for dealing with you know, time series data. You really, in a lot of cases, you only care about the most recent data, right? So you may actually bucket into individual collections. You may have a collection per day or a collection per week, depending on the granularity of data. And then when you need to purge that older data that you don't care about, you can just drop the collection. I know I only touched on that, but like I said, schema design is, I mean, it's kind of an art and a science. But once you get the hang of it, it's wicked easy, and it's wicked cool.
It sounds like if you're using MongoDB in an ad hoc discovery mode, you don't know what your full use cases are going to be, that you need to think about having iterative schema design or alternative schema that you want to discover something preset to the what you want to cycle. That way you don't know what things are going to be. You're using to learn new things that you don't know.
Yeah. I mean, yeah. If you don't know what your use cases are, I mean, you know, try to go with what you know about your use cases and then iterate on that. I mean, hopefully you have you know, the rest of your process is agile and will allow for that. I mean, there are some specific design patterns that you can use if you need to have much more ad hoc type access of data, where you don't know what all the fields are, so you can actually kind of break the model and store it as key value pairs that get indexed. So store both the key and the value and index that as a pair. That's one strategy for doing that. I think they must be serving lunch. People are filing out. I won't stop until you leave. Yeah, Mr. 20 Questions is still here. No. That's good. I like questions. Go ahead.
So in terms of like import tools, so I know you've already talked about that twice. Are there any plans to improve like Mongo import, because it's very limited in what it can do? And on top of that, when I've tried to import lots of data, it tends to fail. And this is like commas delimited files, and sometimes I also have to you know, run some like tab separated stuff to get it to work.
That is actually in development. So we're actually retooling those tools, and it should, I cannot make any promises, but should be part of 2.8. So stay tuned for that. Check out the release candidates of 2.8. I'm not sure if the documentation is up on the new tools, but they should be much improved.
So this question is probably a little maybe too technical, but it's more of a troubleshooting question that I've encountered while so I have Mongo, so I deployed MongoDB, have a replica set. I have a couple of query routers, you know, Mongo has some good there. So I'm loading in some Apache access log files, right? So, but I'm getting stuck. And I'm getting stuck at this error that says, so the name of my database is called web logs, okay? So the error that I'm getting is, and I'm using PyMongo, okay? So I'm getting this fail to open create, or fail to open / create error in this create private map function.
Okay. Let's take that question offline. Okay. But good question. Glad to hear you're using MongoDB. But yeah, hit me up after the talk. We'll talk about that. Any other questions? Cool. Thanks, guys. Appreciate it. Those of you who are left.